Good morning, dear students. So in the last class, we have analyzed the overdamped system. So what is an overdamped system? So depending on the value of the damping factor or the damping coefficient zeta, so we have categorized this damping vibration or damping system into categories. So the first category is the overdamping system or overdamped system, where zeta is greater than 1. Then second one is the critically damped system, where zeta value is equals to 1. And the third category is the underdamping system, where zeta value equals to where zeta value is less than 1. Okay, so we found out the roots of the equation of motion for a damped free vibration of a single degree freedom system, and the roots were this one: S1 equals to minus zeta plus under root zeta square minus 1 into omega n S2. Okay, so it is like this one. So here, as zeta value greater than 1, so when we put the value of zeta greater than 1, so what we will get? So we will get a negative number. Okay, so negative number which is real. Okay, so here also this under root term will be converted to a definite or a real number, and combining with this value of the zeta, so it will be a real negative number. Okay, so similarly S2 will be also a real negative number, so under this underdamping system. So for these kind of roots where real negative numbers are there, so the general solution of the differential equation is given by this way. Okay, so x equals to c1 e to the power s1t, c2 e to the power s2t. Okay, so finally what we have got, so we found out the values, okay, or the expression for c1 and c2 by putting the initial condition. Okay, by putting the initial condition of the displacement and the velocity. So in these two equations, one was the equation for displacement, another was the equation for velocity. Okay, and finally we got the expression for c1, okay, and similar expression for c2, where zeta is replaced by minus zeta. Okay, because c1 plus c2 equals to x naught. So x naught is the initial displacement. So finally, after substituting, so we found the solution to be this one. Okay, so x equals to x naught by 2 under root zeta square minus 1, and this way. Okay, so we found out the solution. So now you can ask me, sir, there is no sinusoidal or cosine, or there is no sine or cosine function. Okay, so whether this equation will be periodic or not. So as because this is only an exponential function, so this is aperiodic. Okay, this is not a periodic uh, motion. Okay, or rather you can say that this system is non-vibratory. Okay, so in overdamping system, the system is non-vibratory. So physically also you can feel the system. So when there will be higher resistance, okay, in against the motion of a system, so then there will not be any vibration. Okay, the motion will be very much sluggish motion. Okay, very slow motion. So so how you will be able to plot the graph in between this displacement and with respect to time. So I told you in the last class that the expression of this dimensionless term x by x naught, because this x is here and x naught is there. So when you will just uh, just move it to left hand side, so you will get a dimensionless displacement or dimensionless quantity, okay, on the left hand side. So if you plot the dimensionless quantity of displacement with against time, okay, or omega nt, so what you will get, so get some exponential curve, okay, for different values of zeta. And from here, this expression, So what you can see that all the terms, okay, what you can see that all the terms of e to the power, okay, means all the exponential terms of e will be negative. See here, minus zeta plus zeta square minus 1, as because zeta value is having what, greater than 1 value, so this term will be negative, isn't it? And here also plus c2, okay, so c2 e to the power s2t, isn't it? So here the s2 value, it is also negative. Okay, so at the very beginning we saw that the two roots are real and negative numbers. That is why e to the power some negative value, and here also e to the power some negative value. That is why this exponential curve will be look like this one. Okay, so they will gradually means comes downward with a curve. Okay, because this exponential curve looks like this one, isn't it? So negative exponential curves. So for different values of zeta, so if you put the values of zeta greater than 1, means 2, 3, 4, 5, like that, so you will get this kind of graph. Okay, so so from this graph what you can say that, so as the zeta value it is increasing, okay, so it is deviating from the stable condition. Okay, because see, this is the stable equilibrium line. Okay, so this is the equilibrium line. So here 0 means what, there will not be any displacement. Okay, so here will be 0.2 unit displacement, so like that maximum displacement will be 1 because x naught. Okay, because this is the initial displacement. Okay, so that is why the ratio is maximum value, it is having 1. Okay, so what you can say that, so since the power of e is negative in both the terms of the above equation, so they both decrease exponentially with t. Okay, and so x decreases as t increases. Understood? So x decreases as t increases, so become 0 at t equals to infinity. Okay, so when t equals to infinity, so the motion, it is 0. Okay, so yeah, so what you can say that in all the curves the system comes to the equilibrium position in nearly an exponential manner, isn't it? So higher the damping, more sluggish is the response of the system, isn't it? Higher the damping, more sluggish is the response of the system. So this may even be seen physically that higher the damping, so more resistance to motion is there, and therefore slower is the movement, as I told you. Okay, so theoretically, however, the system will take infinite time to come back to the equilibrium position. So once it is disturbed from it, and this type of motion is called aperiodic motion. Okay, so this is not a periodic motion. So from this curve, so we can analyze, okay, the motion of a system, as I have told you. Okay, so whatever points just now I have mentioned, so you need to write. Okay, so and you make the notes accordingly. Okay, now let's come to critically damped system. Okay, so what is a critically damped system? So in critically damped system, the zeta value is 1, isn't it? So here the zeta value equals to 1. So when zeta value equals to 1, so if you just put the zeta value in the expression, so what was our expression of the roots of the general equation of motion? So S12 equals to, what was the roots? Minus zeta plus minus root over zeta square minus 1 into omega n, isn't it? So here if we put zeta equals to 1, so what you will get? So minus 1, so it will be cancelled out because 1 minus 1 it will be 0. So minus omega n. Okay, so S12 will be minus omega n, so that is why S1 equals to minus omega n, S2 equals to minus omega n. Okay, so in over damping system, so you found out the roots to be this one, isn't it? But here in critically damping, as because this is having a definite value, that is minus 1, so if you just put it in this expression, because this was the general expression for all the kinds of damping, okay, damping system, so you will get S1 or S2 equals to minus omega n. Okay, so now what will be the solution? Okay, so if you just put it in the general solution, x equals to c1 e to the power s1t plus c2 yeah, there is one important thing, very important thing. Okay, so when the roots, okay, of the characteristics equation are equal, okay, real and equal, then the solution of the differential equation is not c1 e to the power s1 t plus c2 e to the power s2 t, but c1 e to the power s2 s1 t plus c2 t e to the power s2 t. So this extra t term will come. Okay, so these are the mathematical actually expression. Okay, so when you were solving differential equation, so you actually found all these kind of expressions, okay, or the general solutions for different kinds of differential equation. Okay, so by mathematics this expression is like this. Okay, so x equals to c1 e to the power s1 t c2 t e to the power s2 t. So this extra term will come here for this critical damping because the roots are real and equal. Okay, these roots are negative, real and equal. Understood? So that is why, so when we will be putting the value of s1 t, so minus omega n, here also minus omega n we will put. Okay, so let's say this is yeah, so again what you can do, so e to the power minus omega n t, e to the power minus omega n t, you can take it common and it will be c1 plus c2 t. Okay, so under bracket c1 plus c2 t e to the power minus omega n t will be there. So let's say this equation is 8. Okay, means from over damping, so we are actually giving the numbers, so now it is 8. One important thing, that zeta, I told you that zeta, it is it is written like this way. Okay, small exponential symbol, then some head and tail you can give. Okay, but in some of the books, okay, so you will get zeta, it is like this way also. So both are correct. Okay, so zeta like z. Okay, so one tail will be there, zeta. So this way also, some in some of the books you will get this expression of zeta. Okay, it is called as zeta. So here what we need to do, so we need to just differentiate this term because this is in terms of displacement. Okay, so we need to find out the value of we need to find out the value of c1 and c2. So as because these two expressions are there, so we need another equation. Okay, or the in the initial condition, so we will be getting the equation for velocity also if we just differentiate this one. Okay, so what are the initial conditions? So x equals to x naught, same condition at t equals to 0. So x naught equals to 0 at t equals to 0. So initial displacement was x naught and initial velocity is 0 because there was no initial velocity. Okay, so when the body was displaced. Okay, so in both the condition the time was not started. Okay, so the time it is 0. Okay, so here this value we will be putting it here, and this value, yes Manas. Actually auto admission, okay, it is allowed here, and please be on time. Okay, please be updated when I share the link, so at that time please join. Okay. So yeah, so we got two expression for two initial conditions for x and x naught. Okay, so here this expression, so we will be putting it in the displacement equation, and here this expression we will put in the velocity expression. Okay, so how this velocity we will find out by differentiating this displacement with respect to t. Okay, so if you just differentiate, so you will get this one. So this is u into v. So u into v. Okay, so you will treat it as u and it will be v. So first you differentiate this one, so u, so what you will get, c1 is constant, so only c2 will be there because with respect to t you are just differentiating, so t will be dt by dt, it will be 1, only c2 will be there, so e to the power minus omega n t. Okay, now you need to differentiate the second term, this one. Okay, so this is constant, so you need to write it here, c1 plus c2t plus into minus omega n will come out, isn't it? So that is why minus is written. Okay, so minus omega n it is written here, so e to the power minus omega n t. Okay, so if you just differentiate this one, this one with respect to t again, so you will get this expression. Okay, so now you can put the two expression, two initial condition in these two equation. The displacement condition here we will put, and the velocity condition we will put it in this velocity expression. Okay, so what we will get, so when we will put this expression here, so instead of x we will be writing x naught. Okay, and here the t, because t is 0, okay, so e to the power 0 will be 1. Okay, and here this term will vanish because this will be 0, so x naught will be equals to c1. And from velocity expression, so what we will get, so at 0, x dot equals to 0, at t equals to 0, so here we will put 0 instead of this x dot equals to, so here t is there, so e to the power 0, that will be 1, so t2 c2 we will write minus, so here this term will vanish. Okay, so only c1 will be there, and this term will vanish, e to the power minus omega n t, because e to the power 0 will be equals to 1. Okay, so minus omega n c1, so c1 minus omega n. Okay, so this expression you will get. So from these two expressions, so you will be easily find out the value of this one. Okay, so c2 will be what, so c2 will be omega n into x naught. Okay, so value of this one, c2 is omega n x naught, and c1 is x naught. Understood? Now what we will be doing, so we will be putting these values of c1 and c2 in this expression. Okay, so what was our expression, so x equals to this c1 plus c2t e to the power minus omega n t. Okay, so what we will get, so directly we will get this expression, x equals to x naught 1 plus omega n t e to the power minus omega n t. Okay, and this expression is again aperiodic. Okay, because there is no sine cosine terms, so this there will be movement only in one side of the equilibrium position. Okay, so this is not a vibratory motion, and this critical vibration, okay, so this is also aperiodic in motion. Okay, so how this expression actually it is written, so here it is yeah, from here, so this expression is again written. Okay, so how this becomes this one. Understood? So very simple calculation, so only you need to know the differentiation. Here it is written that the value of x in the above equation can be shown to x decreases, t increases. Okay, so here you can see when x is decreased, when t is increased, because minus its sign it is there. Okay, and tends to infinity, isn't it? So it tends to infinity, t will tends to, so when t tends to infinity, so what will happen? So the expression will become 0, isn't it? So it tends to infinity. Okay, so this is shown in dotted line in the previous figure, and it is periodic. So in this previous figure, so you can see this dotted line. Okay, so this is this line is for the critical damping. Understood? So this line is for critical damping. Okay, and what summary actually you can get that these two vibration, that is in the damp vibration of over damping system and critically damping system, the vibrations are not the motions are not vibratory motions, they are aperiodic motions. Understood? Okay, so now let's go to the next one, that is under damping system. Okay, under damped system, so here the value of zeta is less than 1. Okay, and this is the most usual case of damping. Okay, so practically, so we need to design our equipments, okay, or machine tools under this under damping condition. Okay, so where you will get some vibratory motion and which can be isolated. Understood? Okay, so this is the most usual case and most important damping from the design perspective. Okay, design of machine element perspective. Then this system in the case said to have small damping. Okay, so very small damping. So if you just put the value of zeta by taking a lesser value than 1, so what you will get, so this minus zeta plus, because this will be reversed. Okay, because yeah, see, not if you just take the iota, okay, so under root minus 1, so you will have to write like this way. Okay, z, or you can write I also. Okay, so I am writing z under root 1 minus zeta square omega n. So here also the roots were this one, isn't it? So now what I will be writing, So here the roots are complex conjugate, isn't it? And the solution of the differential equation will become what? So e to the power c1 e to the power s1t plus c2 e to the power s2t. Understood? So same expression. So for roots where complex conjugate roots are there, because this is negative, because it is plus, it is minus, so complex conjugate roots are there. So for complex conjugate roots, the general expression for the solution, it is x equals to c1 e to the power s1t plus c2 e to the power s2t. So instead of s1 I am writing here this one, and instead of s2 I am writing this one. Okay. Now the equation in the form is not very useful, and so it is changed to this one. So c1 e to the power c, this expression e to the power minus zeta omega and t, e to the power minus zeta omega and t, it is there. So you can make it common, this term e to the power minus zeta omega and t. So here it will be c1 into e to the power this iota, okay, or j under root 1 minus zeta square omega n t plus c2, because this term you have taken it common, minus zeta omega n t. So e to the power minus j under root 1 minus zeta square omega n t will be remain there. Okay, so now you are having this equation. So by Euler's formula, okay, so you have got Euler's formula in differential equation of motion, differential calculus. So what was that? So e to the power eta a, okay, e to the power eta a is what? So cos a plus iota sin a, okay, or you can write j also. So cos a plus j sin a. So e to the power minus j a equals to cos a minus j sin a, okay. So this is Euler's formula, not in differential calculus. You have got this one in the complex numbers. Okay, so when you have studied complex numbers, okay, there you got this Euler's formula of e to the power iota a or e to the power minus iota a. Okay, in terms of cos and sine function. Understood? So now we will be applying this cos and sine function. So here, okay, by treating it as a and this one, and under root 1 minus zeta square omega n t. So omega n will be treating it as a, just like e to the power iota a. Okay. So now how it will become? So x equals to e to the power minus zeta omega n t. So c1 will be remain same, multiplied by, okay. So e to the power I, okay, I IA, okay, we will consider this whole term, okay, which is connected with this iota, so as a. So how we can write? So cos, okay, because cos a, so cos this term under root 1 minus zeta square omega n, okay, into t, okay, because this whole expression which is attached with this j, it is a, okay. So cos a plus j, okay, so j will come here, j sine a, so sine term and this complete term under root 1 minus zeta square omega n t. Now for this term again we will be writing this Euler formula plus c2 cos a, so under root 1 minus zeta square omega n t minus j, we will write sine a, instead of this a we will be writing under root 1 minus zeta square omega n t. Understood? Now you can simplify this one. So e to the power minus zeta omega n t. So here you can make it common, okay, cos under root 1 minus zeta omega 1 minus zeta square omega n t. So here you will get, and here also you will get, okay. So c1 plus c2, this was common, so c1 plus c2, and this one you can take it common, okay, cos under root 1 minus zeta square omega n t plus here also you can make it common, sine under root 1 minus zeta square omega n t. So what you will get? So c1 minus c2, because c1 and here negative sign is there, so iota is there still, so j under bracket c1 minus c2, because minus sign is there, c1 minus c2, so sine under root 1 minus zeta square omega n t. Okay, so here the constant c1 plus c2 and c1 minus c2 in the above equation are real quantities, okay, so which makes c1 and c2 complex conjugate quantities. So the expression, okay, final expression can be found out because we should know how to calculate these values of C1 and C2, isn't it? So what we will be doing, so we will again differentiate this one with respect to X, and we will put the bound initial conditions, okay, in these two expression of displacement and velocity expression, so which we will be finding, okay. So after that, so what we will be getting, so we will be getting the value of C1 and C2 where it is written that C1 plus C2 and C1 minus C2, these two expressions are having real quantities, okay, real quantities values, real values. So after getting that values of C1 and C2, so the final equation will become like this one, okay. So these three expression, anyone you can write. So the solution for this expression, okay, is either this one or this one or this one, anyone you can write as solution, understood? So these two expressions are actually important expression because most of the problems, okay, so which you will be going to solve will be based on these two expression, okay. So first expression is x equals to e to the power minus zeta omega nt. So instead of c1 plus c2 they have written a, okay, instead of c1 plus c2 as, because they are real quantities, so it is written as a, okay. And same cos under root 1 minus zeta square omega nt, same thing they have written, plus c1 minus c2, instead of iota c1 minus c2 they have written b, okay. This is complex one, sine under root 1 minus zeta square omega and t, okay. So instead of c1 plus c2 they have written a, and instead of iota c1 minus c2 they have written b, okay. So this is one solution. The other solution may be written like this way. So x equals to a1 e to the power minus zeta omega n cos, okay, under root 1 minus zeta square omega n t plus phi 1, okay. Yeah, and here, so means phi 1 is what means after simplification for few terms, so they have merged those few terms into phi 1, okay. So if you just solve this one by, as I have told you that after differentiating and putting the initial condition, so you will be getting this type of expression, okay. So a1 e to the power minus zeta omega nt cos under root 1 minus zeta square omega nt plus phi 1, and here instead of a1 you can write a2, and here instead of phi 1 you can write phi 2, okay. So here you can see that these expressions are sinusoidal or cosine, okay, curves. So where you can say that these are periodic function, okay. So damped periodic function, these are damped periodic function because zeta is there, okay. So one important thing, so earlier what was our expression of general expression of vibration? So a sine omega t, isn't it? So if you compare that expression, okay, x equals to a sine omega t, so which is the expression for a simple harmonic motion. So if you just compare, so what you will get, so this is the amplitude, okay. So here, as because this is damped vibration, so this is damped amplitude, okay. So a2 e to the power minus zeta omega nt is the damped amplitude. So in GATE examination you will see, if you will see the previous question, so it is asked, okay. So in under damping vibration, what is the damped amplitude of vibration? So options will be given, okay. So the correct option will be a1 e to the power minus zeta omega nt, or whatever it is given as amplitude, okay, a. So a2 e to the power minus zeta omega and t, okay. So it is equivalent to the amplitude which was under free vibration of single degree freedom system, not damped, okay, undamped free vibration of single degree freedom system. So a sine omega t. So what was omega? Omega was the frequency. So here this is the omega, okay, and this omega is called as the damped natural frequency because here the system is under damping condition. So under root 1 minus zeta square omega n is the damped natural frequency of the system. It is denoted by omega d, understood? So this omega d is equals to under root 1 minus zeta square omega n, okay. So the natural frequency and the damped natural frequency is having one relation in this damping vibration. Okay, and that relation is omega d equals to under root 1 minus zeta square omega n t. Here it is written omega d equals to under root 1 minus zeta square omega n. So here the oscillatory, yeah, the motion, sorry, this is then natural frequency. Okay, so if you just want to plot this graph, okay, for this expression, so you will get this kind of graphical representation. Okay, so this is the axis for this displacement, this vertical axis, and this horizontal axis, which is mutually perpendicular to these two axes are mutually perpendicular. So this is the equilibrium line, horizontal line, and this line is for this time period t. Okay, or a time, instantaneous time, okay, t. So if you just plot it, so you will get this kind of graph where in each of the cycle the amplitude of vibration goes on decreasing, and finally what will happen, the body will comes to rest. Okay, but after infinite time. Okay, so large time is necessary, and after that time, okay, time period, so the body will comes to rest because the system is having one damper, isn't it? The damping value, it is very low. Okay, in under damping it is less than 1. Okay, the damping factor is less than 1. The damping coefficient, it may be greater than 1, but damping factor zeta, which is the ratio between C and CC, okay, damping coefficient to the critical damping coefficient. So for this damping factor where value is less than 1, so the amplitude of vibration will be like this one. Okay, and here you will get one envelope. You can see the funnel shape envelope you will get if you just join the crust. Okay, crust of all these amplitudes, okay, or of all these cycles. Understood? So here you can say that this is first time period, okay, from this point to this point, td. So this is second time period, 2 td. This is third time period, 3 td. Okay, and the envelope, okay, or the amplitude is how it is decreasing. So it is decreasing exponentially. And what is the value of this amplitude? This is the value of this amplitude, a2 e to the power minus zeta omega n t. So it is also asked in competitive examination there, what is the value of the amplitude in the envelope formed in the under damped vibration. So this is the amplitude. Okay, so a2 e to the power minus zeta omega n t. Okay, what I have told you a few minutes back. Okay, so this is the amplitude. Understood? And what is the time period? So as because you now you are able to find out the damped natural frequency, so omega d is what? Equals to under root 1 minus zeta square omega n. So the 2 pi by omega d will be the damped time period. Okay, so 2 pi by omega d, that is under root 1 minus zeta square omega n d. So this will be the value of this td. Okay, so time period, capital td. So here also this value is td. Understood? So now I think you will be able to just draw. Okay, you will be able to write the general expression for all these kind of vibration, damp vibration, that is over damping, critically damping, and these under damping vibration, and you will be able to plot, okay, the curves, okay, or the graphical representation you will be able to now draw. Okay, and this is one task for you, that in copy, okay, so with your own handwriting, so you need to write all these things very neat and cleanly. Okay, so here, as because these are my notes, so here, okay, some overlapping was also there, because at that time when I prepared these notes, at the time I was also just actually recapitulating all these things, and I was just noting it down. Okay, so generally I used to draw all these things in blackboard. Okay, but this time, so I will have to show my this one previous notes. Okay, otherwise see, to make all these things, okay, it is time consuming, as well as okay, through online it is not that easy. Okay, to convey all those things, okay, to depict all those things in a particular drawing, and this kind of drawing also you will not get in book. Okay, so means where all the parameters may be shown. Okay, so this is, so as it is manual, so I think it is easily understandable for you all. Okay, so up to this much I will be just stopping here, stopping myself here. So up to this much you just study. Okay, and if you find any difficulty, then you can ask. Okay, And after this class, we will be starting, okay, in the next class we will be starting the logarithmic decrement. Very, very important. Okay, so here on the logarithmic decrement, so we are having one experiment also in our lab. So we will be doing this logarithmic decrement. Okay, so after that we will be solving various problems from this damped vibration. Okay, so after that your second module will also be over. Okay, thank you, dear students. So if you have any doubt, so you can ask me. And the previous classes, okay, so I have shared in the Google Classroom, and the notes also, these notes also, this PDF file also I have shared, okay, in the Google Classroom. From there you can download it and you can take it for your own self studies. Okay, thank you, dear students. If you don't have any doubt, you can leave the meeting.
Thank you, sir.
Yes.